All right, so we are looking at page 4 of exam 2, and here we're looking at a couple of mechanisms. Let's take a peek at the top one here. All right, so we've got uh, a phenyl ring, an aromatic ring. We've got a ester group, and it's attached to the oxygen there. All right, and so the importance of this is, remember, whenever we're doing electrophilic aromatic substitution, you've got to check for donating versus withdrawing groups, right? And an ester like this, bound through the oxygen with lone pairs on it there, that's going to be slightly donating, right? So ortho pair directing is what we really want to pay attention to in this case, okay? So let's start it out. Remember, with electrophilic aromatic substitution, we've got to generate a good nucleophile. We've got to generate a good electrophile. So let's go through and generate a good electrophile here. And the way we're going to do that is by using the bromine here, and then we're going to use our Lewis acid catalyst, our iron complex there. All right, we're going to bring in the iron bromide. Okay. Now, I'm just going to draw it, right, with three-dimensional shape, but, that's not too important, right? The important part is coming up here. Where this is going to have a positive charge, this is going to have a negative charge. Now, this is the somewhat deceptive part about, this electrophile complex here. So this bromine here, let me swap this out for red, right? Just for argument's sake, right? My bromine in red there, it looks, oops, sorry. Ignore that, right? So that bromine in red there, it just looks like your standard typical bromine, and you might think that the bromine in blue, right, with the positive charge might be the one that's the stronger electrophile here. But remember, what happens in this case is we are weakening this bond right here, right? That bond in black is really weak, right? Those two bromines right there, they don't want to really be bound to each other right now, especially when one's bound to the iron and all this kind of stuff. So what's actually happening is that bromine in red there is a very good electrophile at this point. And so remember, I'm just going to draw this here. Remember what we could have drawn, and some textbooks and some online sources draw it like this, where that bond completely breaks. And I guess that's not technically incorrect, but where we have this here now, let me get my red marker. I guess it's not technically incorrect to draw this, although it's not really well, I have to be careful what I say here. Either one is technically correct, but you got to show the generation of the electrophile. Let me put it that way, okay? So it's hard to say which one is more correct than the other, and I'm sure it's in some kind of equilibrium, and one of these is favored, and I'd suspect that this one is actually favored in equilibrium, but that's a little bit beyond what we care about. The point is this, right? We have to generate a good electrophile. In either one of these cases, that's what we have, okay? All right, so now we've got a good electrophile. Let's go through and do electrophilic aromatic substitution, right? So we're going to bring in our aromatic ring. I'm going to bring in my aromatic ring right here. Just for simplicity's sake, I'm going to do this ortho. But you could have done it para also in either case, right? So pi bond swings out, grabs that bromine, right? Or, right, we could have grabbed this guy right there, right? Either one of those would be perfectly acceptable, okay? Okay, so let's see what happens here then. All right, so there's my ester group. This is over here, this is over here. We made a bond to my bromine in red, right? And we left behind a positive charge. And this was, right, this is the reason why I added this ortho, right? Just to emphasize the fact that now that since we've got lone pairs on that oxygen, we can stabilize that positive charge, right, by using those lone pairs to form a resonance structure there, right? So this is the whole idea behind ortho pair directing, is that we can stabilize that charge there, okay? Okay, so now we've got to solve a problem. That problem is reform the aromatic ring. So something's going to come in. grab the hydrogen from the carbon where the bromine was added to. So let me grab this guy here, right? So likely what's going to happen, right, is this guy's going to come back in. One of these bromines is going to swing out, right? Grab that. I'm going to reform that ring. So let's follow along here. There's my 6 carbons. There's green, green, ester. Here we are, right? We had bond to red, bromine, and we reformed this right here. We also made HBr, right? Right, we made HBr from that bromine there, sending its bond, right? And then we reformed our FeBr3 here, okay? So there it is. Generate the electrophile, right? Generate the electrophile complex, make the ring swing out and grab, right? And then reform aromaticity. So this would be a good place to pause. I'm going to have to, delete this so we can go on to the next problem here. So if you guys want to pause here and copy this down, that would be, that'd be probably the ideal situation at this point. Okay, moving along. Let me get rid of this right here then. Whoops. There we go. All right, so let's take a look at this problem right here. So we've got a conjugated pi system, and we're adding some HBr at low temperature and at high temperature. Okay. So what we're looking at here is kinetic versus thermodynamic, right? Additions, right? We'll do this. Additions to conjugated systems, okay? Now, in class, we talked about 1,2 versus 1,4 additions, right? And we talked about how that works. But here, I really shook things up. And instead of having 1,2 versus 1,4, now we've got 3 pi bonds instead of the 2, right? So, whoa-ho-ho, right? Good thing we were all sitting down. Otherwise, that could have been tragic there. Okay, so anyway, what does 1,2 versus 1,4 addition mean, right? So we're just talking about, can we take an extra step, right? Kinetic means the fastest product gets formed, right? So you can think of it in a way of the least amount of steps, right? The least amount of steps to get to the answer, right? We can talk about rate determining steps and all that kind of thing. And that's kind of a discussion for, outside of the realm of this video. But we can think about kinetic as being the fastest product form, and then thermodynamic is the most stable product that's formed, right? It doesn't mean that they're necessarily mutually exclusive, but when you have these conjugated systems, we have to be careful about which one gets formed along the way, right? So negative 80 means we don't have a lot of energy around, and if we don't have a lot of energy, that means we're not going to take a lot of steps. So when we do low temperature, right, we're going to favor some. Oh, excuse me for just a second. Sorry about that. Anyway, to recap, what I just wanted to say here is, let's take at negative 80, right? We don't have as much energy, right? We're colder, so we're going to favor kinetic, right? We're going to favor whatever happens the fastest, right? So here is how this is going to work, right? So here is our product. Excuse me. Here's our starting material. Here's some good old buddy HBr. Okay. Pi bond reaches out, grabs this, grabs that. Boom, boom. Right, we're going to put our hydrogen here, positive charge there. Why do we put the positive charge there? Well, it is an allylic carbon, right? It is next door to, let me put this in purple here, right? So this purple carbon right here is allylic. It's next door to a pi bond, right? So we can, in theory, draw resonance structures. But remember, if we want to think about it like this with conjugated systems, with kinetic control, right, we're not going to draw a resonance structure. We're just going to put the carbocation at the most stable position, right? So then all we're going to do, bring in our good old buddy Mr. Bromine there, right? And we are done. Easy, whoops, that should be in yellow, excuse me. Easy peasy, okay? Nice. Okay, so how is the 40 degrees Celsius one going to look different? The answer is the first step. Okay, apparently my computer doesn't want to cooperate with me. Try one more time here. There it is. It's going to start out looking exactly the same, right? We're going to still have an attack. We're going to start out with, the pi bond reaching out and grabbing the H from the acid there, right? So we generate the positive charge, and we got this here. Now we've got some more energy, right? Now we've got some more energy. So what can happen is we can start to see some rearrangement, right? We can start to see some rearrangement from our cation. So let's draw a resonance structure. So now we have this, right? So there is a resonance structure, but we broke our conjugated system, right? If we ended up here, we would, lead to a isolated set of dienes, which wouldn't be as stable as reforming our conjugated system. So let's push another resonance structure here. So we have this, there's our hydrogen up here, and now we've got our positive charge down here, right? Let's go back and just track this along here with some color. So there's purple, there's purple, there's purple, black, 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 red, 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 green, green, green. Okay. Hopefully that kind of made it a little bit easier to kind of track what's going on here, right? Now we've done some rearrangements, we've done some shifting, we regenerated our conjugated system. So likely now the bromine's going to come back in. Boom, 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 boom. Okay. All right, so there we go. Think about what happens with these conjugated systems and, low temperature versus higher temperature. Obviously, the longer this conjugated system is, the more complex the answer becomes, the more side products, right, that can get formed along the way too. So we do have to be careful of that. But go back and let's review about kinetic versus thermodynamic, and that should help with this. Okay, that's the end of page 4, and I will see you in page 5.